All right. Okay, so that's a Schottky diode. The way you can recognize a Schottky diode is the symbol makes kind of a boxy S. Backwards S, but makes an S. The next type of diode is the Zener diode. The Zener diode is designed to operate in reverse bias. So normally when you have a diode and you operate in reverse bias, it's going to drop all of the voltage. Well, the cool thing with Zener diodes is they're specifically designed to operate at a range in reverse bias. So if you have an 8-volt Zener, that means in forward bias, it's going to drop 0.7 volts, but in reverse bias, it's going to drop 8 volts. Yep, they just put it in backwards. We have diodes in all sorts of flavors here. 13.2 volts, 8.1 volts, 5 volts, 6 volts, 12 volts. The Zener diode is one of the first steps that we can use to regulate power. One of the cool things with this, guys, as long as there's that much voltage, it will drop that amount. If it goes over that amount, it'll keep this amount. So if you have it in an AC signal that's changing from 0 to 10 volts, we put it in an 8-volt Zener, it's going to drop everything until it hits 8 volts, and then it's going to stop. And then the rest of the 2 volts will be dropped across the rest of the circuit. And then once it drops below that 8-volt threshold, again, the Zener diode will drop everything. So it does its best to hold that voltage at whatever it is. So when you put them in power supplies, you could put in a 12-volt battery, run it through the system. You could put it in an 8-volt Zener and a 4-volt Zener, and you could split that down. What I would do is I'd put the 8-volt Zener in, and then I'd put the 4-volt in parallel with that guy with a couple other resistors and kind of make a loaded voltage divider, which then can split my power out. And it'll keep it fairly constant. It helps eliminate a lot of AC noise when the values are above the voltage. Because normally if you have any kind of power fluctuations, you would see them, like up on the high end, you would see your power fluctuations, you would see a little bit of ripple in this. The Zener diode doesn't care once it gets over a certain threshold, so even if it's doing this is our threshold, you're going to have flat power. So it's one of the first steps to regulating power, is it maintains this voltage. Doesn't care what happens above it. And that's really important, because if you have circuits that's designed for a specific voltage, as you guys have noticed, when things start deviating, your values farther down the line end up not coming out close enough. So if you have something that varies by 5% in your power, your output values are going to vary by at least 5%, probably more, because it's going to affect things farther on down the line. And that's one of the things we'll find out is when we get into AC, is AC raises all sorts of hell with calculations, because it is hard to dial into an exact specific frequency and an exact specific voltage. So your error is going to be a little bit larger in AC than it is in DC, because things are constantly changing. All right, so with the Zener diode, we operate it in reverse bias. It has a specific voltage drop that it operates in, and internally it does what it needs to do. It either increases or decreases its internal resistance to maintain this voltage. You get more current, it's going to adjust itself to maintain this 8 volts. That's its whole job, is to maintain whatever value it's rated at. If it doesn't have enough voltage, it's going to grab up every volt it can to keep at that level. So nothing else will get anything. So in that instance, if it's below the threshold, it's going to act as an open. There will be no current flow, and there will be no voltage being dropped anywhere in the circuit, only across the Zener Once we exceed its level, its breakdown voltage, then we will start to allow current to flow through our circuit. It's going to take all of it until it meets the threshold. These are the 3 common used diodes that you guys will see. There are a couple other special case diodes, but again, they're so few and far between. Unless your company actually is going to use them, you'll never see them. So we don't worry about talking about them. Okay. Any questions about the Schottky, the LED, the Zener, base diodes, anything like that? Okay. One of the cool things that we're going to talk about is the application of Zener, or of diodes, not just of Zeners, but of any diode. The primary function of a diode is used to help regulate power. And by regulation, we want to remove variation. So in DC, there's not a lot it does other than stopping current flow or allowing current flow, depending on how you have this set up. You could have a power supply or something that when it gets a positive voltage, you want this circuit to shut off. If you get a negative voltage, you want a buzzer to go off. Okay, so like with our bridge circuit, you could have the wires coming out of the bridge where the middle resistor was connected to a diode and a speaker. When it goes to a positive voltage or negative, depending on how you put your diode in, you could have it. So when it's positive, it does nothing. When it goes negative, your speaker goes off. Basically saying your load's out of whack. You need to realign your load. But the biggest portion where diodes come into play is in AC circuits. This is just a very brief intro to what AC is doing. So in a DC wave, we have time, we have voltage. This is a DC signal. For all amounts of time, it is 1 voltage. AC does this. So we have a constantly changing voltage. We'll go, like I said, we'll get into the specifics of this after the final next week. So AC we use because it's easy to transmit. It doesn't require a lot of power. It doesn't require a lot of things. All these lines that we transmit, it's AC. We get the wave, we get those waveforms going, and we can send them for miles. DC has a very, very short range of being able to transmit before it starts losing voltage farther and farther down the line. I think it's like a 300 or 400 foot length before you start to see significant drops with your DC power. AC, we can go for miles.
So do we use AC to transfer all the energy and turn it back to DC?
Most of the time, yes. So AC comes into the house, but 99% of the time you convert it to DC. There are motors that run on AC, the lights are all AC, but if you plug anything in and it has any kind of a box, it's converting it to DC. Mm-hmm. Yeah, if you were to open those up, you would see inside is a power supply. You would see some inverters. You would see diodes and a couple capacitors and a resistor and then maybe a Zener diode or two regulating everything out. Yes. Yep. Yep. Yeah, DC is what's in a taser. Okay? So yeah, you're running a line across to allow something to get tased. AC, like I said, AC, it's not as volatile as DC is. It travels easier, and you don't have as much loss. That's the biggest thing. Is it requires a lot of energy and power to maintain a DC signal than it does an AC. Plus, AC is made really easily. Like DC, it takes a lot. It takes, for example, with my experiment, it takes a potato and a copper nail and a zinc nail. For a motor, it just takes 2 magnets and a wire. Like, it's a whole lot easier to make AC and to make a lot of it versus the DC. But DC is easier to learn than AC. Okay, so we get these different signals. In DC, like I said, it doesn't do a whole lot other than like with Zener diodes with specific voltage drops. When we get a signal like this, what we have, so I'll draw these in here. We have our input in green, so our signal is going up and down around 0 like this. This is our in. What a diode does is it allows voltage in one polarity. So in this case, we have a positive polarity attached to the positive of our diode. So it's going to allow that voltage through. Okay? When it gets to the negative cycles, it shuts it down. All the voltage will be dropping across the diode. And what we'll see is this. They're absolutely necessary. They are the first stage for filtering an AC signal back down to a DC signal. In a way, yeah, it's going to drop everything until it hits its value, and then it drops that max value regardless of how much it goes over the top. So if we had a Zener diode in this system, we would see another drop coming in. So this is V out. The capacitor is going to follow this. Or sorry, the diode. So this is V diode, this is V out. So we're going to see a 0.7 volt drop across the diode, and then when it hits this negative, it's going to drop everything. The output is going to have 0, and then when the positive comes back up, we'll see it drop back up to the 0.7 volts. Which, we may want. In this case, we either want the positive or we want the negative peak of these guys. This is, like I said, this is where it gets fun with diodes and AC, is converting it back into DC power. But this is the end of next semester. But this is, like I said, this is the primary use for regular diodes. Any questions? Let's look at a circuit that combines all these components together. So resistors, capacitors, and diodes. It'll be fun, I promise. Okay. So the first things we have to do is we have to figure out what is happening. And because we have a capacitor, resistors, and it's DC, we have to be concerned with time. If we were just to plug this circuit in and it just said find the voltages, we would have to assume that the circuit's been on, it's been running, this capacitor is fully charged, is our first step. So once this capacitor is fully charged, what's going to happen? What's the voltages? 0 across everything except for the capacitor. The capacitor is going to drop all 25 volts. But we want to find out what's going on as this capacitor charges. So what we want to do, we're going to make another chart of what's going on with all these different components, and then we're going to graph them. So we can have a visual representation of what's going on. So we have 1 tau, 2 tau, 3 tau, 4, and 5 tau. We'll make this easy. What we want to know, how much time has gone by, what's the voltage of capacitor 1, the voltage of diode 1, the voltage of R1, and the voltage of R2. So as we go through this, again, we need to analyze this at each individual stage. At tau equals 1, tau equals 2, 3, so on. So first thing we need to solve for is what? Tau. What is our tau? Now our tau is resistance and the capacitance of this guy. So this guy is connected up to what resistors? R1 and R2. So that's going to be the total resistance that we take. So 2.2 and 1K. So we'll have 3.2K multiplied by 100 microfarad. Hmm? 320 milliseconds. To save time, I'm putting in my columns what units I'm going to be using. Let's switch because that one's light. Okay. So first tau is 0.32. Okay, how much time elapsed after 2 tau? How much? Okay, how much time elapses after 3 tau? Again, we're just taking tau, multiply it by the stage we're in. Okay. 4 tau? And 5 tau, fully charged. Okay, we're going to use the values of the tau. We're going to use these exact values, so it's not going to be quite fully charged, but we're going to be able to see what these guys drop. Okay, so the first thing we need to solve for, well, as with any of the circuit, we have to analyze the circuit and find out, is this diode going to be in forward bias or reverse bias? It's in reverse bias, okay? And how do we know it should be or should not be in reverse bias? It's a Zener, because we're given a Zener voltage. So a Zener diode is supposed to operate in reverse bias.
Does that mean that it'll always drop 6 volts without that?
If it has 6 volts, yes. So that's the biggest thing. If there's 6 volts in the circuit available, this will drop it, and nothing more.
Does that mean that resistor has to match that voltage?
This resistor is going to match this Zener, because it's in parallel. Everything that's not dropped across these two can be dropped across R2. Yeah. This is here just so we have a place for the extra voltage to go to. All right. So first thing we need to look at is our first time period. So we're looking at when time equals 1 tau at 0.32 seconds. We need to solve what is the voltage of the capacitor, what's the voltage of the diode, R1 and R2. So first thing is, how much voltage do we have across the capacitor? That'll be the hardest calculation. We go to our equation. The voltage of the capacitor, V final plus V initial minus V final, the quantity of, times e to the negative t over tau. So we know, what is this ratio going to be? -1. So that saves us a little bit of steps because we have 0.32 divided by 0.32, which gives us the -1. And we also assume that we are at 0 charging up. Unless it says otherwise, assume starting at 0. So voltage of the capacitor is equal to, what's the final voltage? 25. I was blocking it, so. Oh, you got the final answer of it? Okay, so when we get that value, what is it? 15, is that it, or is there decimals? 15.803. So if we have 15 volts being dropped across the capacitor, how much is left? 10, roughly, 9 and change, 9.2 volts. Okay? We have 9.2 volts being dropped across the rest of the circuit. Is this diode operating fully in reverse or partially? Fully in reverse. So how much voltage is the diode dropping? 6 volts. Okay? If the diode's dropping 6 volts, how much is R1 dropping? 6 volts. And R2 is dropping everything that's left. The cool thing is, and I will show this with you guys later, is I will bring in a scope and a circuit, and we can actually construct this thing and watch it. And we can have all the signals displayed at once to watch all these things changing. All right, so at tau equals 1, we have 15.8 volts across the capacitor, 6 volts across the diode in R1, and 3.2 volts essentially dropped across R2. Now we want to look at time equals 2. So again, we want to solve for the voltage of this capacitor. So again, this guy's still charging up to 25 volts. We're starting at 0. Only this time, it's e to the -2. So what do we get for this voltage? $21.167. Okay? How much do we have left over? 3.383. So if we have 3.383 volts, how much is being dropped across the diode? All of that. So R1 is dropping that. How much is left to drop across R2? 0. There will be a little bit of voltage on that because we still have a little current, but it's going to be negligible. We're talking less than probably 50 millivolts at the most. It's still operating. There's still a little bit of current flowing. Partial. because this thing is choking it down. Okay, now we want to go to 3. So at 3 tau, it's going to be the same equation, only to the negative third power. Okay, what is our capacitor voltage? For the third rung. 23.755 volts across the capacitor. How much is dropped across the diode? How much across R1? The same. How much across R2? 0. Okay, tau equals 4. .542 volts, which means how much is being dropped across the diode and resistor 1? And how much is dropped across R2? 0. And the last one, I'll just write this one down for you guys. 832, which leaves 0.168 and 0 volts. So the idea behind this exercise is we're getting you guys used to using the formula for 1, and for 2, this is a circuit analysis. We're not just, we're moving on from just, okay, we have one option that can happen. We have to understand now we have 5 different points in time that we should look at. Unless we're given specific time frames, have an idea of what this is doing. Okay? At some point, yeah. I mean, you'd still need, this voltage is going to have to drop somewhere, and you don't want it dropping on your supply. So in this instance, for the timing, no, you could get by without it. But with how the circuit's set up, you're going to be loading up your supply, which could short things out in the end. Okay. Any questions with how we got any of that data? Okay. What we want to look at now is what would that look like if we looked at it on a chart, on a graph. Come on. Can I power it or not? There it goes. So that is what the data looks like. Except for I do not have the diode on there. Yeah, the diode would follow R1. So hooking up to our oscilloscopes with this, even in DC, we could use our scope to look at DC power, and we would see these curves. We'd have to zoom in quite a bit based on the time, but we would see the scope or the capacitor. We would see that curve charging up. We would see this diode and the resistor come up and then drop off. And again, we'd see R2 come up and then just drop off to nothing. So this is exactly what we would see on the scope looking at this. And that's what we'd be looking for. The biggest thing with our caps is, again, is we want to watch this graph. And it should follow this curve. We should have the 86.3%. We should have 99.3% there. We should still have those, and we should still be able to trace them. 25 is the max, and all the different values in there with tau. We could do this with other values besides tau, but tau just makes it really easy to solve. Now, we could have something built in the circuit. So this, essentially, at this point, this is our delay. Okay? We're turning on the system to our machine. We're flipping the power on. We want it to start charging up the batteries and getting everything powered up. And we want to make sure we have power. And then quickly we're going to do something. We're going to turn on a fan or whatever. And then that signal is going to go away. We've hardwired in now a command. We turn it on here. And now we've introduced a hardwired delay into our system. Because like I said, there's sometimes you're going to want to turn something on, make some sort of a noise, and then shut off when it's okay to use. Okay? Cars. When you first turn them on, what do? They ding at you. They make all sorts of obnoxious noises. Exactly. Okay? We want it to go, put your seatbelt on, put your seatbelt on. And then we want it to start. And then we want it to go off. And then restart, later on. But the idea is when we first turn it on, this is hardwired in. You're going to turn it on. It's going to start dinging, making noise. And then those are going to go away. Unless there's another problem that then says, okay, turn that signal back on. Yeah. But the only time you want to see your check engine light turn on is when you first start your car. But yeah, that's the idea here. So we're teaching you guys the basics. This is hardwiring a delay. In the programming classes, you guys are going to code in a delay. This just ensures that things are ready to go. Because a lot of times, while you're still waiting for the power to come on, because it does take some time, it's not instant, you want power to come up so that when you kick on a motor, or you kick on a driver, or you kick on a fan, or you kick on a light, that their power is there to support it. Especially if you want it to play a happy little tune. If you've ever noticed, like on the little toys or whatever you buy from the dollar store or whatnot that make noise, what happens when the batteries start dying? Whoa! Whatever sound it's supposed to make doesn't get made anymore. And so you want this to be able to have things happen when there's the power for them, when there's the time for them, things like that. That's the biggest part of these circuits, is they are set up. They're set up this way so you can have hardwired delays. So I apologize if you guys go back and watch the video, you won't be able to see that. It is in my notes that are on Moodle, so you can go back and reference it, but there's just going to be a black screen at some point, or this is going to be sitting there. So just fair warning. All right. That is analyzing circuits using capacitors, diodes, and resistors. One of the last things that we're going to cover, we'll start that up tomorrow, is we're going to cover relays. The basics of how relays work, okay? What are they used for? Why do we want to use them? Things like that. After that, we're going to start getting into the math portion of this week. This is getting us ready for understanding and being able to solve AC circuits. Huh? Yes. You can. That's the thing here is once we're going to learn how to go back and forth between radians and degrees and all that stuff. But when you're working on these things, you can work in radians or you can work in degrees. Most of the time, what we work on is in degrees. 90% of the time, anything we do is degrees. Yeah, calculus. Everything leads back to calculus. So, tomorrow, like I said, we're going to talk about relays. Then we are going to get into trig, just so you guys are aware. We're getting into trig, right triangle math, Pythagorean's theorem. We're going to learn how to convert numbers back and forth between polar and rectangular, adding and subtracting, multiplying, all this fun stuff. We'll talk about degrees versus radians, angular velocity, and that's it for the week. Yes. Yes, your calculators will be your friend. Guarantee it. Any questions? Yes. There's an actual quiz for it. It should be popping up. If it hasn't yet, I got to go. The quiz is there. Where to take the quiz hasn't popped up in Moodle yet. Yeah. So they have to get it turned on. So I got to go talk to Marcy. She will get that turned on for us. Again, that'll be due Friday. Get it done before the final. Really, but you have Friday. I have time set aside to do it because part of it is I can't be in the room while you're filling this out, according to ISU policies. So that's why we've done it before. Is we've just gone down to the computer lab for the first part of our lab time. And you guys can do it down in there. If you don't want to do that, then that's fine. You can do it later. It just has to be done when I'm not in the room. Because again, it has to get processed before I can see any of this information. It's supposed to be confidential. So, any other questions? Okay. Have a good night, guys.